Good afternoon. Ever get a chance to hit the food trucks out there? Well, I hope you don't have food coma. Who's ready for some math? I see a few brave souls ready for some math. Well, there's nobody better to talk about math than Britta Weber. She is going to teach us all about the latest and greatest in search technologies with BM25. So, without further ado, Britta.
Hi. Hi, can you hear me all right? Is that good? Okay. So I'm Britta. I joined Elastic, the company, about 3 years ago as a developer. And I am now mostly working on Elasticsearch Core. Okay, and today I'm going to talk about BM25, which is a method to order your documents or to score your documents if they contain natural language text, such as tweets, mails, articles, and so on and so forth, given a free text query, some keywords. And the reason why I'll be talking about it is because from the next major release of Lucene, we'll be switching the default, which is now TF-IDF, to BM25. And that means that the next major release of Elasticsearch, too, because it's based on Lucene, will switch the default from TF-IDF to BM25. So I thought now would be a good time to learn about it. Okay? So usually when you go and ask people, what's BM25 actually about? They go and sometimes say something like, oh, so BM25, yeah, that's that probabilistic approach to scoring, right? And then everybody nods their heads. And some feel a little ashamed because they don't really know what it means. So at least this is what I did, right? So, and then a colleague asked me, and I know a little bit about probabilities. So I thought, OK, I should check it out. So here it is. This is BM25 in all its glory. OK, so some of you might be fortunate and be able to parse such an equation in little time and immediately see what all the parameters do and what this is all about. Frankly, my first reaction was more like that. So I found it a little scary, right? And I mean, in general, you might wonder, what's actually so hard? Why do we have to come up with such a monster for text scoring? And I think it's worth spending at least a few minutes to remember why scoring of text is so tricky. Okay? So why is that so complicated? So first of all, many of you might not even have that problem. Many use Elasticsearch mainly for analytics or for storing data that actually has hard criteria which you can use to filter your data. So you have, for example, I don't know, some items that you store and you look by ID, or you look by customer name, or you look by date. So something that's actually a hard criteria. And you filter on that, and you don't actually need the ordering of the documents. And this is especially true if you have this analytics use case. So that's easy. But it gets a little more tricky when you look at text. And the major problem is that language is fuzzy, right? So language is verbose. Many words that you see in it don't actually carry any meaning, right? It's ambivalent. Some words have different meanings. Text is usually about, well, different topics, and it's not quite clear what it's about, and subtle things going on. So this is one problem. So you got this fuzzy text on the one side. But then on the other side, you as a user, you have to decide how to actually formulate your query. So what are you actually looking for? And this is, again, you have to do this with natural language because, well, you look in natural language text. So there's no clear way to actually formulate your query. And as an example, think, for example, you're looking for an intern, right? And say you're lucky. You have many applications. You have this whole database of people that want to apply at your company. You might be tempted to look at the self-description, too. So what people write about themselves, right? And I'll say, on the one hand, you're looking for somebody who's a quick learner, who works hard, who is well reliable, enduring, and you have all these criteria that you want to match your candidates on. And on the other hand, you have this text. So how do you actually put all these criteria that you have into a query? They'd probably end up typing something like, well, you're looking for a hardworking, self-motivated masochist, something like that. And this is it's a severe reduction of the actual information need that you have. That is, you want this quick learner that works hard and so forth. Okay, so in the severe reduction of this information need, this makes it so hard to actually find what you're looking for. So every search application that you have that actually tries to find the best documents or the best matches better makes use of these few keywords as good as possible. That's why this is so complicated and why I'm going to talk for 40 minutes about it. All right, so what am I actually going to talk about? So I hope that by the end of this talk, you will all understand exactly what this whole equation is all about. So understand all the details and what all these parameters do. So this is one thing, and it's actually not the hardest part. I'll talk a little bit about the history, or actually I'll talk a lot about the history of BM25 and how it came into existence, and especially about the mathematical concepts behind it. So we're doing a little bit of math. And frankly, this is not super relevant for most of you in practice. This is more for your entertainment, because it's really fun to see where it actually came from. Plus, you will afterwards know, hopefully, why it has the label probabilistic. So I will try to convince you that switching to BM25 is the right thing to do. This is actually the hardest part of this talk. We'll see how that goes. I hope you're convinced. And then finally, I hope that after this talk, you'll be able to impress all the people that were not in this talk with your in-depth knowledge of probabilistic scoring. So, we'll see. OK, before we talk about BM25, just a quick reminder of what TF-IDF, the current default, is actually all about. So we stick with this rather artificial example of we're looking for an intern. Okay, we're looking for a self-motivated, hard-working masochist. And then we want the application to order the applicants by searching with these keywords in the self-description, and we're looking for the most relevant documents. So this is what this is called, the relevancy. Okay. So the only evidence that we actually have that some application is relevant for this text query is the term frequencies. Okay, so what we go is we actually take these keywords that we typed in our search engine, and we count how often they occur in the self-description. And the number of times a word occurs or a token occurs in a self-description, this is called the term frequency. So remember this is going to be important. Okay, so we count this. And now how do we turn this into some relevancy or into some score? And in TF-IDF, there's basically three things that we do. So the first thing is we say, OK, term frequency means more is better. TF-IDF assumes that the more often a term occurs, the more relevant this document is. And we don't just sum that up. What we actually sum up in Lucene is the square root of the term frequency. So we go through each search term, find out how often this is, take the square root, and sum that up. And this curve, so the square root curve, this is what you see on the right-hand side here. Right? So it decreases not linearly, but it decreases, increases, sorry. So that's actually not a good score, it turns out. Say, for example, somebody types the probabilistic ranking principle or something like that. So they type something like the or a or who. Now, these are words that occur in nearly every English document, and they occur many times. So if you assume that more is better, then all documents that have, for example, the, and this will be all of them, will get a pretty high score, and we don't really want that. So instead, what we want is that common terms weight less. Okay, and this is called the inverse document frequency. And this is the plot that you see on the right-hand side. So we assume that the more often a term appears in a document, in your corpus, the less important it is. And this is a weight that we multiply to this term frequency to adjust for these common words. Okay, so what we do is we basically multiply the upper thing with the lower thing, and then sum that up. Okay, this is still not enough. In TF-IDF, we also assume that if we have a long document, so we have two documents, one is a tweet, the other is a book. One mentions our search term once, the other two, then we assume that the tweet is probably about this term that we're looking for, but the book, if it has 1,000 pages, probably not, right? So we say, okay, longer documents are probably, given that they have the same term frequency, less important. Okay, this is called the norm if you ever look that up. And again, you can plot this on the right-hand side, so this just decreases. So the longer the document is, the lower the score will get. And if the term frequency is higher, of course, it'll get up again, but this is the basic idea. Okay, so that's TF-IDF. And then there's one last thing that you have to consider. So Say, for example, you're looking for several keywords. You're looking for 2 keywords, say, I don't know, holiday in China or something like that. And you got 2 documents. One is a blog about my holiday in Beijing, and the other is the economic development of Sichuan from 1920 to 1930. The second document is probably not as relevant for your holiday, right? But it might contain the term China more often than the other one. So according to TF-IDF, because we assume that the more often it occurs, the more relevant it is, the second document might actually score higher if you use a Boole query with should clauses. So what we have in Lucene, or also in Elasticsearch, is sort of a hack that's called the coordination factor that makes sure that documents that have more matches are rewarded and documents that have less matches are penalized. Sorry? I don't understand the word, sorry. Sorry? Oh, all right. Oh, yeah, sorry. Okay, so this should be holiday and not travel. Yeah, sorry, messed up the word, so replace travel with holiday or the other way around, and then you'll get it. Thanks. Okay, sorry for that. Okay, so that's basically a hack to get around this problem. Right, nevertheless, TF-IDF has been successful since the beginning of Lucene, or the dark ages, as a colleague of mine puts it. It has been the first scoring, it has been the default ever since the first release. It's pretty well studied. It's rather easy to understand intuitively. And so I call it a one-size-fits-most algorithm, right? You cannot tune anything, but it's sort of okay for most use cases. So you might wonder, well, what's wrong with it? And there's actually nothing wrong with it, but it is somewhat a guess. So, for example, I said that we sum up the square root of the term frequencies. And this is actually an educated guess of one of the developers who just did run a couple of tests and found that, hey, yeah, if I take the square root, it gets a little better. So let's use that, right? So it's ad hoc. Somebody sat down and thought, this makes sense intuitively, let's try it out. And the question is, hey, maybe we can do better. Okay, so now we talk about BM25. And I said we'll talk about the history a little bit. And the beginning of BM25 is probably what you would call the probability ranking principle. And I'll give you the abridged version of that. It states that if retrieved documents are ordered by decreasing probability of relevance of the data available, then the system's effectiveness is the best that can be obtained for the data. Which, at first glance, seems as a rather trivial statement, right? We say, okay, so we want to order by relevancy. So what's cool about that? And there's actually 2 things that are exciting about this. So we're talking about probabilities here. So if we manage to match our intuitive understanding of relevancy to some mathematical framework of probabilities, then number 1, we immediately have the chance to deploy prior knowledge of our data or of relevancy into our scoring and maybe make the scoring a little better, right? Now that's cool. And the other thing is that if we manage to map this to some mathematical framework, we can immediately harvest the work of countless mathematicians that have done the work for us already. We don't have to prove anything, right? So this is super exciting. Okay, so in the next 20 minutes or so, I'm going to talk about how this probability ranking principle actually led to the final equation that we saw in the beginning. So we're going to do a little bit of math. And in order to do that and not bore you, I want you all to think as mathematicians for the next 20 minutes only. Okay, and by that I mean, number 1, let go of all practical considerations, right? You don't care how much heap it takes. You don't care how many CPUs you need, right? You don't care about that. We'll get to that later, but forget about all that now. And number 2, think of yourself as super smart, way beyond 2 standard deviations. And I'm not saying that because I think all mathematicians are arrogant or something. No, that's not why I'm saying it. Saying it because it is sometimes easier to look at equations and be assured that, yeah, you're smart enough, you can fill the gaps later and you can figure it out. And I'm actually sure you can, because it's not super hard stuff. So, okay. So we want to estimate some relevancy, or the probability of relevancy. And we'll start off with a simplification. So we say relevance is binary. It's either 1 or it's 0. Okay? And note that this doesn't mean that we cannot order our documents. What we're trying to do is we're trying to estimate the probability that the relevancy is 1. Right? And this is still a float, and we can still order by that. So that's the basic idea. And now the second idea is that we say, okay, so say we had some data set that already tells us something about how relevant some documents are to our query. Maybe we can use this to learn about the relevancy of the next documents. So basically what we're trying to do is we have some sort of intern, so that's a little figure here, and we can give them a query and a document, and this intern will tell us, okay, this is relevant or this is not relevant. And this way we can get some data set. And actually we need a few of these interns to do that all day, right? To get a proper data set for that. So we have all these interns, they click all day, and then what we end up with is a set of all documents, some of which are relevant and some of which are not relevant, for different queries. So now, how can we actually use this to get a better scoring? Or what would this look like in math? So in math, we would say, okay, we want to know the probability that the relevance is 1 for a document, given some query and some document. So this P here means what's the probability, R is the relevance, we want to know if it's 1. This vertical bar means, okay, given that, and then we have on the other side document and query. And just to give you an idea what this really means, so what this expression actually means is, it means you need some sort of matrix, right? On the one hand, you have your documents, on the other, you have your query, and then for each document and query pair, you actually want to have a number. And that's the number that you actually use for ranking. And now, this is nice for considering it, but of course, it doesn't make a lot of sense because A, you don't know all the queries, and you don't know all the documents that you might ever have. So this is a pretty huge matrix. It doesn't really help. Right? And the whole idea of starting to do math here is to try and convert this huge matrix that we have into something that is more useful, something that we can actually store. So what we can do now is we can try to apply a bunch of mathematical tricks. So first of all, of course, we have to incorporate the fact that our document is not just a document, but it's a set of, well, term frequencies. We want to incorporate that. And we want to see, well, maybe we can get to something more easy. Okay, and this is the part where you have to think of yourself as super smart. Because here be, yeah, okay, so from that point on, here be math. I'm not going to go through all the steps that are actually needed to get to something that is really useful. So you can do that actually on the plane, or you can read it at home when you're bored. Don't read it before you go to sleep, because it's super exciting. So not that you sleep, don't do that. If you actually want to know what happens here, you can read this paper. So this is an exceptionally well-written description of what you have to do to get from this expression to something that's actually useful. That's the probabilistic relevancy framework, BM25 and beyond. So if you want to know what's going on, check it out. It's really, really nice. But what's the useful result that we actually get? So we had this huge matrix, but we cannot probably ever get that. So we do apply a lot of tricks and a lot of stuff. What we end up with is something like this. And the first thing that you might notice is that on the right-hand side, it doesn't say probability anymore. It says weight. And the reason is that at some point, we got rid of this whole probability thing. And we don't actually need that. Because the only thing we need is something that would order our documents the same way that we would order them if we had the true probability. OK, now we say we sum up over only the terms that are in the query. This is something we also didn't have before. And we sum up the log of these 4 new probabilities. And what those actually mean, so the first one is, in the denominator, probability that the frequency is some particular value, given that relevancy is 1, or in the denominator, given that the relevancy is 0. So this is this orange thing here. And you can, again, think of this as a list. Okay, so you have a list for every term that is in your corpus. So for example, hardworking. And you have a list for the different frequencies. So hardworking is 1, hardworking is 2. And then again, for given relevancy is 0 or 1, and you have a number for that. And you have this for each, if you have that for each term in your corpus, you can just plug this into this equation. And then the blue thing here, these are just two numbers. This is for the case that a term does not appear in your document at all. And then again, it might not appear, but the document is relevant, or it might not appear, but the document is actually irrelevant. And these are, again, just two numbers. So if we were able to acquire these lists with these probabilities, and then plug this into this equation, we would get something that is actually pretty close to this probability ranking principle that we saw before. Right? That's the basic idea. And now all the development of BM25 is basically about how do we estimate all these probabilities. Okay, so, and there's basically two ways to do that, or two assumptions that we make. Number one, it's called the binary independence model, and it's actually a pretty dramatic assumption, because we say, okay, we assume that a term only appears or in a document or it doesn't. So term frequencies is either 1 or 0. And this is most of the time not the case in the documents that we're looking at, like in articles or mails. You wouldn't expect that. But for tweets or chats, this actually makes a little bit of sense, right? So think of that use case. So what we end up with for each term, so this is now for one term, we have a set of documents, some of which are relevant, some of which contain the query term, and some are relevant and contain the query term. Right? And we would have this for each term. So now consider we had that. And we have that because we have all these interns that click all day on our data and tell us if something is relevant or not, and we know if the term exists or not. So suppose we had these numbers. What we could actually do is we could go and estimate these probabilities that the frequency is 1, given that the relevancy is 1, and that the frequency is 0, given that the relevancy is 1, and all these other things from these sets. And I'm just giving you these two examples here. So probability that the frequency is 1, given that the relevancy is 1, is just dividing the number of relevant documents that contain the term by all the relevant documents. And then plus some smoothing parameters, which I'm not going to talk about. Right? This is the basic idea. And the same way you can get that the frequency is 1, or that the term occurs in a document even though it is irrelevant. And then you take these probabilities that you can actually get from your data, just plug them into this weight equation that we saw before. Okay, and then you end up with, so if you just do the math, you end up with what's called the Robertson-Spark-Jones weight. This is something that you might see every now and then in the literature. And this is just really so if you take these r plus 0.5 divided by r plus 1 and plug this into this thing, this is what you end up with. And the little r and the little n and the n and the r, these are really just the counts in these sets. Okay? So the basic idea in theory is you have all these interns that click all day. You get these numbers for little n, little r, n, and r. For each of the terms, you plug this in this Robertson-Spark-Jones equation, and then you get a number for each of your terms in your corpus. In theory, this is the idea. If you have an unlimited supply of interns, and again, we're still in math mode, right? We don't care if that's actually feasible. Now, actually, we do. So you probably don't have that, right? So what do we do now? So I make a rather counterintuitive assumption, is that we say, okay, so relevancy, we don't actually have that many relevant documents. Maybe we can get away with just assuming that the relevant documents are negligible and set them to 0. And the fun part is, even though this is counterintuitive, it actually leads us to something. So this leads us to the IDF weight of BM25. And that is what you see here. So it's just the logarithm of number of documents minus documents that actually contain the term. So it's the document frequency we saw before, divided by number of documents that actually contain the term. Okay, and just to give you an idea what this looks like, so this is actually the scene implementation of this, and this is on a logarithmic scale. So on the x-axis, you see the document frequency. On the y-axis, you see this IDF weight. And this is similar to what we saw before for TF-IDF. This is actually the TF-IDF counterpart. So it decreases, right? And then at some point, and this is again on a logarithmic scale, if you plot this there, you see that it actually decreases further the more common the words get. So in comparison to TF-IDF, it doesn't have this S shape, right? This blue curve here. But again, it's pretty similar. It's a similar concept. Okay, so I'll give you our monster again, right? This is the part. This is the IDF part of BM25. And again, it's similar to TF-IDF. Okay. So now if we go on, so we considered that a term occurs or does not occur in a document. But actually, this is not really true. We want to consider this too. So the number of times something occurs in a document. So what does the number of times something occurs actually tell us about relevancy? And in TF-IDF, we said more is better. But for BM25, the first question is a document actually about some term just because it occurs in the document? And this property, whether or not a document is about a term, this is called eliteness, if you ever look at this in the literature. And the basic idea is, we don't say TF, or term frequency and relevance, is directly linked, but we first figure out if a document is about a term, and then we say, we try to estimate how eliteness and relevancy are related. Okay, but let's first talk about eliteness. And just to give you an example, if you look, for example, at Wikipedia and you look for tourism, right, there's lots of articles that contain the word tourism. Like, for example, each article of a country would contain the word tourism, but it doesn't mean that this document actually is about tourism. Right? Like, for example, I mean, there's articles about dark tourism or health tourism that are actually about that, whereas the article about the country is not really about tourism. So this is an example for when it's elite and not elite. Okay. So how does this look like? So we have two cases. The document is not about the term. In practice, what we would assume is that the frequency is probably rather low for documents that are not about the term. So on the right-hand side, what I plot there is an x-axis, again, the term frequency, and then on the y-axis, the probability that, to observe this term frequency in documents that are not actually about it. So eliteness is 0 here. And again, you can think of this as a list. I'm just plotting it here because it's nicer. And then, on the other hand, you might have documents that actually are about the term, and you probably in practice would assume that the term frequency for this is higher. Again, this is something that you might assume. It might not actually be the case. It's something you would have to study, but might be the case. Okay. And so again, we can go and think of this as lists and then have to store all these lists, but we don't actually want to store these lists. And then in the 70s, somebody came up with the idea of say, hey, maybe we can find some analytic function for that, and proposed to actually model this as a Poisson distribution. And I'm just showing this here. So this would be the actual analytic function for the equation for the Poisson distribution. And the cool thing about this is that we don't have to store each of these values, but we only have to store one parameter, this lambda. And we would have to store it for eliteness is 1 and eliteness is 0. So for each term, we have 2 more parameters that we have to store, and not endless lists for each term frequency. Right? So another question is, how do we get this lambda? Or how do we get these values at all? And again, so we take our intern, and we tell our intern now not to say if a document is relevant or not, but instead we give them a term, and we give them a document, and we ask them, is this document actually about this term, or is it not? And then this intern can tell us, oh yeah, it is about it, or it is not about it. And this way, maybe we get some data, and maybe we can get a good estimate of that stuff. But actually, this is much more tricky than saying if it's relevant or not, because it's not really clear if something is about this term, or is it not about this term. So opinions on that might vary, so you would have to train them better, which means you would actually need a lot of interns to do that. Right? So that's tricky, but for now we don't care. We just assume we have them. So now we have an idea of what eliteness is. I suppose we knew this already. We still need a relationship of frequency and relevancy, because this is really what we want, right? And the idea is to yet have another distribution, a probability of eliteness given relevancy. It's in this case. And again, this is simply similar to the binary independence model. We can think of our documents as a set, and then we have some of these documents are relevant to some query, and some documents are elite. And again, we have some documents that are elite and relevant. And then maybe we can just use the same trick as before and try to estimate from these numbers what this probability actually is. And this is, again, just a number, right, per term. Okay, so go and estimate it from the data, which unfortunately means that we need even more interns, right? Not only those that tell us if it's elite or not, but also what the relationship between eliteness and relevancy is. I mean, it could potentially, right? That's the basic idea. Okay, but we don't care. So what we try to do is, we still don't do the math, we don't care about this problem. And we say, okay, so we have this relationship of frequency and eliteness, and we have this relationship of eliteness given relevancy. So we try to combine these two to some probability of frequency and relevancy. We plug this into this weight equation and hope that something good comes out of it that we can later on use. Okay, so again, here be math. This is actually not tricky. Again, you can look at this paper. It's a very good description about how this actually works. And I'm not going to show you the details, and there's not much to it. So let's hope we arrive at something that's good. Unfortunately, we don't. So we get to something that's actually too horrible to put on the slide. And I'm not making this up, so I could put it there. It's not complicated, but it's annoying to explain. It's messy to write. And I quote from this paper, what they say is, well, this is a messy formula that you get. And furthermore, we actually don't have a good way to estimate all these parameters, right? And it's a little bit of a bummer, because I mean, we go through all this trouble and do all the theory and all these computations, and then we get nothing out of that. That's a shame. And so how do we get to BM25 then? And so what happened was, and that was in the 80s or 90s, the developers of BM25, and I quote again from a different talk, took a leap of faith. And in my opinion, that's actually the major accomplishment in this whole development of BM25. Not the math that you saw before and all that stuff, but actually taking a leap of faith and still trying to extract something useful of all this math. Okay, so what was this leap of faith? Well, they asked the question, okay, so we have this horrible thing that we cannot actually make something of, but we could still ask the question, if we were actually able to get the exact shape, what would it look like, what kind of properties would it have? And you could say, okay, so it starts at 0, that's something we know, it increases monotonically, and it approaches a maximum asymptotically. And the maximum, and that's the cool thing, that would actually be the IDF that we computed before, right? So maybe we can just make something up, something that looks similar. We don't really care about the exact result. Okay? And that was this leap of faith, just trying to figure out something that's similar and see if that works. And what they then proposed was to say, okay, so we use this weight function here. We use the frequency divided by the frequency plus some parameter. So this is this k parameter, or sometimes it's called k1 when you see it somewhere. And what this does is it starts at 0, increases monotonically, reaches a limit, and in this plot, this is just to show the shape, so don't worry about the numbers here. The important thing here is that the influence of term frequency is actually limited. Right? To approach this maximum at some point, and more is not better. At some point, it doesn't matter how much more terms you have in your document. It's also sometimes called a saturation curve. And this is the major difference between TF-IDF and BM25, because in TF-IDF, the influence of the term frequency just grows and grows and grows, right? So, plus you have this parameter k that would, in theory, allow you to tune the influence of your term frequency in your scoring. All right, so to go back to the equation that we saw before, so we saw this first part, this was IDF, and now what we did was actually the second part here, the blue thing. That's the saturation curve, and this influences it limits the influence of the term frequency on our score. Okay, and then finally, so far when we did this Poisson distribution and that stuff, something I didn't say is that we actually assumed that our documents have the same length, right? But they really don't, at least not most of the time. And we want to incorporate this too. And then I don't really have a good iteration at this point, unfortunately, but what the idea is that we tune this k parameter further with the lengths of the document. And what we do is we interpolate lengths between 1 and the document length. And then there's one major difference between, two major differences between TF-IDF and BM25 here. So one is we have the option to actually interpolate length. And the second is we don't actually use the actual document length, but we use the document length divided by the average document length, which is rather nice because it means that we sort of put the document length in perspective. All right, and then again, how this would look like, just for one term. So you have this B parameter, which you can set. I mean, you can set it to 1, which means document length has full influence. You can set it to 0, which means it wouldn't have any influence at all. So this is similar to this blue curve here. And then again, in comparison, I mean, this is actually pretty similar to TF-IDF, right? So this is for TF-IDF, where we actually multiply it with the whole score with this thing. That's a similar thing. Just the only difference is you cannot tune it in TF-IDF. OK, so it's the final part. We're done. Now we know how BM25 works. All right, so this is all the different parts, and this is what they actually mean. So, is BM25 actually probabilistic? And so I talked a little bit about how we did many approximations, in particular this leap of faith in between. We said, OK, so this is, we don't actually look at the probabilities at all. We just assume something. But in fact, all the parts where I said here be math, there was actually also lots of approximations that were made to this initial assumption. So that's one thing. The other thing is that even if you try to get the exact probabilities, it's actually super hard to get these probabilities right. And people have been banging their heads on that for several years. Right? So this is actually not something that people do in practice. Or at least, I'm not sure. If you ever heard of that, it's cool. I'm not sure everyone does that. So from another person, I said, OK, so BM25 is more inspired by this probabilistic approach. Right? So whenever someone says that, you can try to be smart and say, oh, no, it's more inspired. Yeah. OK, that's the basic message here. OK, a short history. So development of this started somewhere around in the 70s. Okay, so this whole thing about the Poisson distribution for terms and this Robbins-Buck-Jones weight and the ranking principle, this was all in the 70s, right? And then when you see between 1980 and 90, there was not so much going on. That was the part where people were banging their heads against this monster and trying to figure out how to get something out of that. And then there was this leap of faith in the 90s. And the final Lucene implementation, or what the Lucene implementation is based on, is the publication about the track where Okapi retrieval system participated. Okay, so that was the final. And then 1999, we had the first Lucene release. So that was after that, right? I mean, BM25 wasn't super popular then, but still. I mean, they used TF-IDF as their default scoring. And then it took another, well, yeah, 12 years, basically, to actually implement BM25 properly in Lucene. And that was a Google Summer of Code project by David Demystified, who was tutored by Robert Moore. And that's actually an exceptional piece of work. It's awesome. So he not only implemented BM25, but he also implemented some other scoring algorithms, like language model scoring and divergence for randomness and all that sort. And he made it in a way, and that's really cool, that you can exchange these things. So even if you index, you don't have to re-index. If you use these basic scoring methods, you don't have to re-index. You can just try out the different one on your data. And that's pretty cool. OK, now we're in 2016, and now finally we're having BM25 as a default tool. Right, so it's just to give you an idea of what the time frame here is. OK. And now finally, and that's the hardest part, will I get a better scoring with BM25? I mean, there's a few advantages, definitely. So this frequency cutoff helps a little bit. So first of all, you will have less influence of common words. I mean, we removed, per default on Elasticsearch, stopwords were removed previously. Now it's not so anymore, right? Which might influence your score a little bit already. This might become a little better with BM25, because these common words actually less influence now. Or also word packing will have less influence now. People try to put keywords very often in the documents to appear on top. Right? This is automatically reduced by BM25. We can get rid of this cohort factor hack. We haven't done that yet. So actually, if you use the next major release of Elasticsearch, it'll still use this cohort factor hack, probably. It's going to be a few months, so maybe we can remove it until then. I'm not sure. If not, then there is this index setting that you can use to just switch that off. All right. Then other benefits. So some people like to try and tweak their parameters. Not sure if you actually have to. So if you actually want to go and tweak your BM25 parameters, first figure out if you actually need to, because these defaults usually work pretty well. And if you don't actually have data to measure if your scoring is getting better or not, it's probably not worth tweaking that. Right? But if you want, you can close your index, update your mapping in Elasticsearch, reopen it again, use the new parameters, and see if something's happening. So in this paper that I was showing you several times, what the authors also say is that actually this whole framework, this mathematical framework, allows you to get a better idea how to implement or how to incorporate non-textual features in your scoring. Although, to be honest, I cannot tell you much about the details there. If you want to know more about that, go and read the paper. It'll allow you to maybe make it easier, not guess so much about how to add, I don't know, all sorts of features into your scoring method. OK, so a little bit of warning. In TF-IDF, because we automatically say that shorter fields have more value and longer fields have less value, you got a sort of an automatic boost for your TF-IDF. Okay, so this is not so anymore, because BM25, as I said before, puts these lengths in perspective and first divides the length of the document by the average length of this field. So this automatic boost for your title fields, for example, in articles, might not be as high anymore. And you might need to adjust something if you now rely on this automatic boost. Okay. So is BM25 better? So literature says so, challengers says so, users say so, developers, Lucene developers say so. One of my colleagues actually went, so Conrad Beiske, actually went and did an experiment on Wikipedia. Right? It's not actually approved, but he's just playing around with it and checking out if this actually worked. And he found, yeah, it works a little better for what he's trying to do. If you want to know, you can go to this blog post, BM25 versus the Lucene default similarity, and the follow-up. That's actually also a pretty nice description of BM25. But we cannot actually say if it's going to be better. It depends a lot on the features of your corpus. So it's hard to answer that question. OK, if you want to know if this works for you or not, as I said, you can try it out. You can close your index, update your mapping or your settings, reopen it, and then see if something changes in your scoring. OK, now here's some useful literature. So this is basically the stuff that I was reading for preparing this talk. This is some other stuff. So this book, Introduction to Informational Retrieval, this is awesome. If you never read that before, it's really good. It's a very good introduction to all that stuff. And then, of course, this probabilistic relevance framework. That's a super paper. The original paper, or the Lucene implementation, it's actually based on Okapi at track 3. It's a paper by Robertson et al. If you want to know the actual details, what's going on, that's the best source. Or you can also go and look at the Lucene class directly on GitHub, if you're into that. OK. And that was it. Thank you. OK.
Thanks. I hope you all learned something. We have time for a few questions if we got some. Start right here.
Thank you first for the talk. It was interesting. I had a question. You mentioned that the first implementation of BM25, you don't need it to set it up at index time. You can do different similarity measure at the query time. I'm wondering why do we have, in the current setting, you have to define it during the index time. I'm wondering if it's going to change.
Yeah. So the thing is, I mean, so it's a certain kind of stuff that we need to store on index time to actually make the similarity work. So for example, for TF-IDF, we store the norms and the norm is the length of the field. We have to store that at some point. Now, the way this is implemented right now with BM25 and TF-IDF is such that all the default implementations for Lucene store the norm in the same way. Right? The problem is that if somebody defines their own similarity or uses some plugin or something, they might also want to store this norm in a different way. Right? But we don't know if this is a default similarity or not. Or actually, we didn't implement that yet. So this is why you have to define at index time what kind of similarity you use. But you can later on still change the parameters or switch to one of the other implementations or the default implementations for Lucene. But you cannot switch from one of the default implementations to Lucene to something completely different, something that is outside of Elasticsearch. Does that make sense?
Kinda, because the raw material, I don't know what happens to the norm. If the norm is based on the lengths, we could save the lengths and directly calculate the norm later on. Because the raw material is term frequency, lengths, document lengths, or field lengths, and collection frequency.
Yeah.
If
So to
you
be
have
honest,
this tree, you can calculate any of these similarity measures.
yeah. Yeah. So to be honest, we have an issue open to change that, maybe to make it more flexible, right? Because originally the idea was that you would be able to store different norms, right? So if somebody implements their custom similarity, they might decide to just have a different norm, in which case you would be screwed up if you switch from that to BM25.
Yeah, if you save the lengths, the norm is just one division. It's,
yeah. We could enforce that, but it's not how it works.
Also, I had another question. You said that BM25 is like 10, 15 years old, and we are switching to BM25 now. But there is a language model that came a few years later on, and many studies show that language model, if not better, is comparable to BM25, and it's much easier to tune. It has only one parameter.
Yeah.
It's more mathematically solid and easier to understand.
Yeah.
Why not switch to language model directly?
Yeah. So the thing is, so I'm not actually a Lucene developer, right? So I can only sort of hear what I hear. So the reason why they decided to switch to BM25 is when they actually, when they test analyze, as Robert at least told me, they check on the data sets that they have, all the different scoring methods, and they found that BM25 is across the board a little bit better than everything else, right? But it's really tricky to say, okay, this is actually better than language model scoring, or this is actually better than that. So we're not actually doing research on that. We sort of rely on what the community says. So
Yeah, the research community uses language model.
that's language model, yeah. Yeah, the scene developers are conservative. As I can say about it. I'll keep it in mind. Yeah. I know.
Thank you for the awesome talk. Really, really great how you explained some of the math, really made it approachable. I know there's a couple different variants of BM25, and in one of the variants, there's actually the potential for probability to be negative. So if a document does not contain a term, it is potentially more relevant than something that contains a whole bunch of terms.
Oh.
Which variant of BM25 was actually implemented in Elasticsearch, and are you doing an absolute value so that you can never go below 0?
Yeah, so actually BM25 is the only thing, so this raw BM25 is the only thing that is implemented right now per default. If you want to use something else, you've got to go and plug in your own similarity. And about the zeros, yeah, so what we do for IDF, for example, in the original thing, could go below 0. And Lucene, what we do is we actually add +1, so it only goes until 0, and then never further down. Yeah. Yeah, so, sorry.
All right, thanks, Britta. Be available for a few more questions if people want to approach you.
Yeah, so I'm going to be in the AMA if you have more questions.
Thanks.
Okay.